So let's look at an example, and this is a very simple example. You can think about the simplest possible second order differential equation that is familiar to you, and that's the equation that we have written up here, y double prime plus y equal to 0, and we know that the two linearly independent solutions to this homogeneous differential equation are the sine and cosine functions. And so we provide two initial conditions here, y0 equals 1 and y0 prime at 0 is equal to 0. So you can solve this problem analytically, and you would see that with 1 as the initial condition for the value of the function and 0 as the slope, it picks up cosine as the solution. So the exact solution is cosine, and its amplitude is 1 because the value here is 1. All right, so we have that exact solution. And so to solve this numerically, we can rewrite this equation, y double prime equals minus y, and then since we want to write the whole thing as a system of first order equations, we follow the recipe that we had before. We define a vector big Y with components capital Y1 and capital Y2. Capital Y1 is defined as y itself, and capital Y2 is defined as y prime. And then we can write it as a system as we have written before. And so let's say that the domain of interest is from 0 to 2 pi, and we have a simple cosine wave solution. And so at this point, you have written the equations in the system form, and you can discretize it and integrate and obtain solutions using different numerical methods. And so let's turn to looking at those solutions as plots. Let's look at those plots, and once we have looked at those plots, we can come back and look at quantification of the error that we observe from these solutions.